Hello everybody, welcome back to another concrete design video. This one's going to be super easy. It's on T-beam analysis, and this is just an intro video, but we're going to be talking about the theory behind T-beams, what they are, where you find them in concrete structures, and how to analyze them. And I think the best way to start is to just cover the basics of the one-way slab and talk about what is going on in the system and how T-beams are involved. So for this specific one-way slab that I've drawn down here, we have a configuration where the slab is supported by beams, which are then supported by columns. And the key takeaway from that one-way slab problem video that we did previously is that this slab is transferring load primarily in the direction that the beams are sitting for this example, based on the length in the east-west and north-south direction, right? Now, once this beam has taken this load, it's going to transfer it to the columns. And this beam is going to be taking a tributary area of that slab and taking responsibility to transfer that load to the columns. And for analysis purposes, we're understanding that this concrete slab system, beam and slab system, is monolithically poured, or in other words, cast all together. And we have to analyze the contribution of the slab with respect to the beam as well. So this beam and slab combination is called a T-beam, which pretty much in simple terms is when the slab or the flange is extending on both sides of the web. And you also have edge beams in slabs as well, where you only have one side that has an extension of the flange. Pretty much the main takeaway is you have tributary area and you have a T-beam shape that is being extracted from that tributary area. Now, what are some key takeaways for analysis in this segment? If the slab was continuous, you're going to have negative moments at the columns. You're going to have positive moments at the supports. But for our problem, we're going to be considering when we have a positive moment section. And another takeaway for this segment that we're looking at is the compression block or our neutral axis. Our neutral axis can land in either the flange or it can land in the web. Now, what's the difference? The difference is if it lands in the flange, then you have a uniform, easy to calculate rectangular area. But if it lands in the flange, or the web, sorry, you need to calculate the contribution of the segment in the web and the entire flange. That's the main takeaway for these types of problems. And when it is in the flange, it's super similar to what we've done previously with rectangular members, except this B value is now going to be the BF, or the flange length, because that's what is important for this compression block zone. And we know that all this other concrete is in tension, is going to be neglected anyways. So no matter what the shape is that's going on below that neutral axis, we know that we can take BF times A and be good for analysis. Alrighty, so let's look at this problem. We have a typical cross-section for a properly reinforced T-beam, and we have three 20M bars in the bottom tensile face with an effective depth of 650 mil, and it wants us to determine the moment resistance. It gives us all of our fun factors, which we worked with previously. Now, the first thing that I want to do is simply write down our factors. So we have alpha 1, which is 0.8, and beta 1, which is 0.9. And we know this when you have an FC prime between 25 to 40, these values are going to be approximately 0.8 and 0.9 respectively. And if you want, you can go to the code and calculate it yourself if you feel like checking it out. The next thing we can take out is the information about the reinforcement. So an area of a 20M bar is going to be about 300 millimeters squared, which means that our total area of steel can be 3 times 300, since that's the quantity of steel. And that gives us approximately 900 millimeters squared. Now the next thing we can also do is determine what that tensile resistance is for that bottom steel. So we have phi s AS times Fy. We know this like the back of our hand now, 0.85 times the area of steel, millimeters squared, times Fy, which is 400 newtons millimeter squared. Millimeters are going to cancel out. You're left with Newton. and that gives you approximately 306 kilonewtons. What else do we know? We know that CR is equal to TR, and if we rearrange this formula, we're left with an A equals to this, and this whole top segment is TR. Therefore, A is going to equal to TR over alpha 1 phi C FC prime B. But this B is unique. It's unique for these problems, and that's what we need to remember. If our neutral axis is inside of this flange, that means that we can assume that BF is 1100. Why is that? Because if it is in the flange, that means our compression block is strictly in the flange as well. And this A value will represent the depth of the compression block. And we can simply take that area. So let's assume that we have B, or the neutral axis, in the flange. We're going to take this as BF. So TR is equal to 306 times 10 to the 3. That's newtons. All over 0.8, 0.65. FC prime, 25 Newton millimeters squared. And the BF value, 1,100. And all of that is going to equal to approximately 21 millimeters, which is less than 100. Less than 100, which is the width or the thickness of your flange, meaning that our assumption is correct. And we can actually proceed with this problem because this calculation is accurate, right? That's the main takeaway for these T-beam problems, is you need to understand where your neutral axis is landing. That's really the main objective to this whole theory and problem. Wherever your neutral axis is going to dictate how you solve for that area of your compression block. Now solving, obviously, for the moment resistance, we have 306 times 10 to the 3. The D value, which is given, 650, minus 21 over 2 for A. And you're left with a value of approximately 196.2, or 196, sorry, kilonewtons per meter. Kilonewton meter. Oof, a lot of slurring there. My bad. But yeah, that's pretty much the problem. And that's the main takeaway for these T-beam analysis problems. Just figuring out where that neutral axis is. In the next problem, I'm going to show you what happens when it ends up in that web.